Right. So here is setup for today. So we have some linear function which we are trying to learn. So in particular, we have our hypotheses, which are half spaces. In RD. And we will pretend that these half spaces are homogeneous. So what does that mean? So formally it means that your H is just so look at vectors W in RD, and for every vector like this, you have a half space. So you have a half space W inner product X. Yeah. So that gives you half space. And how does it give you a hypothesis? But you just look at the sign of this thing. So it's just sign of yeah. And why do I say homogeneous? Because there is no additional bias in it. Yeah, so in last class we had a B plus B, so it's just double transpose X. Yeah, there's no additional term here. So in particular for X equal to 0, this quantity is 0. And and now you might ask that what if our true half space has an additional B? So then you just increase your dimension and work in RD plus 1. Yeah, so if you had the real thing look like this, then you just pretend that your vector X look like X and then 1, and your W look like W and then B. So I join a 1 at the end of X, a B at the end of W. Yeah. So at the end of every single training example, I will put down, and then I will just work with these homogeneous half spaces in RD plus 1. So that's exactly the same. Okay. So yeah. So therefore, I can pretend that my half space looks like this. Yeah. So we have not forgotten the bias, just that we have absorbed it inside the X. Okay, I'm going to just clear that. Yeah, why we can remove the bias. Okay, so yeah, so we just work with these things. And from last class, we remember that initial dimension of this thing is what? No, t plus 1. So plus 1, no, sorry, t, no, you were right, t. So t plus 1 was equivalent to c, but so this dimension is d, but yeah, so therefore this suggests that you should be able to learn on this you should be able to learn this class both in the realizable case and in the agnostic case, using our initial dimension theory, right? But you can do that as long as you can learn the ERM. So this means that so if you can learn ERM, so empirical risk minimization on this class of functions, then you can learn efficiently. Yeah, and both in realizable and agnostic. And yeah, because whatever we did also works for agnostic, so works for both. Let me say a few words about how many samples you would need. So I did not go too much into this earlier, but essentially it looks something like d over epsilon log d over delta. So it looks something like this for realizable, and d over epsilon squared log d over delta. We need a little bit more. Yeah. So roughly speaking, this is what it looks like. Okay, you will not get this result from what we did in class. What we did in class was a bit weaker. to get this exact bound, you need a little bit more work. So in the book's appendix, you can find how to get this exact bound. Yeah, but okay, even though we did not prove exactly this, we prove something a bit weaker. But you can just remember this one here for a second. Okay, yeah, okay, so if you have an ERM, then you can learn using these many samples. So this how many samples you need? By the way, what's epsilon delta? Epsilon delta is the epsilon delta of back learning. That epsilon delta. Yes. Yeah, so you need these many samples if you have ERM. And okay, now question is that how do you get ERM? Because here you have an infinite family, so you cannot just go one by one. Okay, so first let's look at the realizable case. Okay, so here we will show that you can get ERM quite easily using linear programming. Does anyone here know linear programming or does not know linear programming? You don't know. Okay, but that's fine. We'll just tell you. It's very easy. Tell you in 2 minutes. So a linear program is something where you have a bunch of linear constraints. Let's think of them as less than or equal to constraints. Let's say you have 2x1 plus 3x2 at most 5 and x1 minus x2 is equal to 7. Maybe you have some constraints like this, and then maybe you want to minimize or maximize an object. Maybe you want to say that you want to minimize 7x1 minus 8x2. Yeah, so you have some objective here, and you have some constraints here, and you want to ask that, okay, what is the smallest value I can get of this thing, subject to my variables x1, x2 satisfying these constraints. Okay, so that's where the L in linear comes, because these constraints are all linear inequalities, and the objective is also a linear function. So yeah, so you have some linear program. Yeah, and the thing is that the only thing you need to know for today is that you can solve anything like this. So anything like this can be done efficiently. By the way, in this class, I'm not getting into details about what efficiently means. Efficiently has a mathematical meaning. So if you are interested, you should just look up what polynomial time means. Yeah, so again, these are not. This is another course about this. But yeah, so yeah, just Google the words polynomial time and you'll see what efficiently means. But for now, just think of it as something fast which can be done. Yeah, that is enough for this class. Okay, great. Okay, so now the question is that can we cast our ERM as something of this type? And essentially, it's not very hard. Maybe someone already sees how to do this. Right. Okay. Okay. So maybe let's take an example, right? So maybe you have. So you're given a bunch of training examples, right? So remember, I said we sample some data, some training data, and then we try to find the best fit hypothesis. Hypothesis which minimizes the error. So the reasonable case, you know that the error can be made 0. So what does that mean? So you have a bunch of examples x1, y1, x2, y2, maybe 2 examples. Remember this like so you have 3 examples which came to you, and let's say you're living in 2 dimensions. 2D. And then maybe your examples were. Okay, I'll erase this. That's fine. So maybe your examples were so 2, 3 had the label +1. -1, 8 had the label -1. Maybe 7, 5 had the label. So these examples can be. Now you want to ask that can I produce a W? Can I produce W1, W2? So that I get 0 error on all of these examples. Right? So yes, so what do I want? I want that 2W1 plus 3W2 should be positive. Right? I want that minus W1 plus 8W2 should be negative. 7W1 plus 5W2 should be positive. Right? Now this looks very familiar, right? This looks very similar to what I wrote earlier. You have some linear equations. The only slight trouble here is that these are strict inequalities. Right? So you don't, ideally you want to do strict inequalities. Earlier we had these inequalities. Right? So if we did not care too much about the strictness, then I could just say that, okay, I just make inequalities and I will just maybe minimize some dummy object. So you say minimize, I just put any object any character. Because I don't even care about minimizing anything, I'm just trying to find a W which fits up. Just write any object, maybe just put 0. So okay, so if you are happy with inequalities, then this is enough. We just solve the LB. But let's say you're not happy with inequalities. Let's say you really think that, so in this sign thing, you really want that. For a positive example, if a label is positive, then W input at X should actually be positive, and label is negative, W input at X should actually be negative. Then you need strict inequalities. So then, then what do you do? So there's a trick which will take care of this. So there is another trick already.
Add some slack.
No, but I need to make this exactly positive. So, no, but if I have a slack variable, then I need to make a slack variable to also be strictly positive.
Yes.
Then by the same code.
Or I can just take some epsilon and make this inequalities like not strict. I mean greater than equal to, and then half the epsilon every time I don't get epsilon.
Yeah, exactly. Yeah. So these tricks can be done. But so maybe I will tell you one other trick, which is famous one, and that is important for a different reason also. What you say works, but I'll tell you a different way. So in a different way of doing it. So the trick is to look at this quantity gamma, which is the smallest. It's basically the min of yt times w input x. So min overall w. Okay, so one fixed w is this. For fixed w, this is the smallest of these things. Okay, so which is kind of a bit fancy. So all this is saying is that for these things, because remember here the y is positive, right? Here it is negative. So here I'm looking at 2w1 plus 3w2. That's what this is. And here look at the negative of this. So here this is w1 minus 8w2. This multiplied this sign. So so here look at the smallest of these things. Smallest of these things after making them positive. So I just put a sign here so that this becomes positive. And so look at the smallest of these things. So this is the smallest thing, right? And now if we want everything to be away from 0, then this gamma better be positive. Right? Gamma better be positive. Fine. Okay. Good. So now what I will do is that I will scale everything. So I will look at W prime, which is W by gamma. So when you do this scaling, what do these things become? So claim that after you do the scaling, okay, so for every t, yt times W prime in a product xt will always be at least 1. This will happen. Why? Because you divided everything by 1. Right? You divided everything by the smallest of these things. Okay, so yeah, so we divide by the smallest of these things, and even the one which is closest to 0 becomes 1, and everything else becomes more than 1. Yeah, so we just enforce this constraint. Yeah, and now we just forget about gamma, right? So gamma does not play any role. It's a bunch of equations. So I can just throw all of them. I can just work with these equations. Yeah, and that's it. Yes, but basically just saying that I put a 1 here. That's it. Partially, that's all it is. When this becomes simple. But yeah, W prime are just variables, right? I can call the variable whatever I want. So essentially, it's
And in the realizable setting, I can always find a solution.
yeah, exactly. Yeah. So this may be the most simple way of doing it. Yeah, and the thing is that this quantity will be important later. So that's another reason for saying all this. So okay, so maybe so maybe I'll say why it should be important. So maybe it is this. So let's draw a picture, right, and see what is quantity inside. So you have this 2D plane here, and in the end, after solving all this, we get some equation, right? I get some line. Maybe this is my line. This line is W inner product x. Maybe this side is positive, this side is negative, perhaps. Now suppose I have some training example x2. Maybe it's here. So now I want to ask that what is the geometric interpretation of W inner product x2? Any idea? Okay, so let's guess, right? So if my xc was this line, then W inner product xc is 0. So kind of the bigger it is, the further it is away from the line. That's kind of the idea. So yeah. Okay. Yeah. So that's the idea. So in some sense, what is gamma telling me? Gamma is telling me that how close is the closest training example to this one. The minimum or all training examples of this inner product. So so perhaps the simplest way of thinking about it is that suppose I want to normalize W and X just for 1 minute. For 1 minute, let's pretend that xt has norm 1. So let's pretend this. So then I can pretend either actually. By the way, okay, just for another cute observation. I claim that I can always pretend that my W prime Okay, now W prime, I always pretend that my XTs are normal. This is always okay to see. Why? Because remember, my goal here is to look at the sign of W in product X. So, so even if I normalize either W or X, the sign does not change. So yeah, so I can pretend if I want that the norms are 1. Yeah, we are not pretend it, but let's say for 2 minutes. So if I pretend this, then what is W transpose X state? Then this is just the projection of W on X state. Right. So here is a line XT. We'll look at this line here. And there's some W somewhere, right? The W is going on, the W is normal. So then this is just the projection. This part. Right. Yeah. Okay. And what if I normalize the other way? Let's normalize the other way. So if I normalize W, let's say pretend again. Something pretended that. Then what would I get? Yeah. So then I project. Okay, I see somewhere. So then I project this X on the top. And it's the same thing. Yeah. So let's say go here.
Then it's a distance.
Yeah, exactly. So then, yeah. So this thing here then is W transpose XT. And since you notice that this line and this line are parallel, because this is because this normal. Therefore, this thing is actually in the distance. Right. So yeah. So in general, yeah, what I'm trying to say that okay. So maybe now I write but formally what I'm saying. I'm saying that the quantity W in a quadrant X divided by norm of X. The norm W is the distance from hyperplane. Distance of X. Yeah, so this is a hyperplane, and this quantity here is the distance. Why are divided by norm W to make the norm of W to be 1? Yeah, okay. But even if it is not 1, this quantity is still exists. Okay, so always divided by 1. Okay. Yeah, so that's kind of why this is important. And so this was when W in a product X is positive. If it is negative, I just multiply by y. So in general, this is the distance. Okay. So that's kind of also why this thing is important. So this shows up here naturally. Okay. By the way, okay, a trick question. Can I assume that norm of W is 1 in the setup? Can I assume it or can I not assume it? I cannot assume it actually, because here what I'm assuming is that the that the minimum of this quantity is 1. That's what I'm really assuming. So So yeah, remember what are we doing, right? I'm looking at the minimum of the numerator and dividing everything by that minimum, right? So yeah, so whatever final W prime I have, that will satisfy that yt times W prime xt uh, is 1 for the smallest. Yeah. Yeah. With the smallest thing. So that may not be compatible with with minimizing norm with the non W equal to 1. They may be 2 different things. So there is 2 scalings at play, right? One is the scaling of W, which makes the minimum of the numerator 1. The other is the scaling where I want to make the norm 1. So they may not be the same scale. Yeah. So here you cannot assume that the non-W is 1. However, if you look at the setup, then what this tells you is that the smaller non-W is in the end, the larger the minimum distance of a training example is from the hyperplane. Because now notice that if you look at the setup, then minimum over RT of YT W number xt by non-W is just non-W, it's just over non-W. Right? Because the numerator is 1 by design. Yeah, so this is exactly what non-W. So it means that if you're after solving all of this, the non-W ends up being large, then your training points are close to this hyperplane. If your non-W is small, then your training points are far. Yeah, at least the worst case training point here, that one is either it's close or far away depending on non-W is bigger. Okay. So that's kind of also why we did all this work, because then you have this nice interpretation. But okay, we'll go over this in detail later also. Hopefully it's clear. Okay, so as such, we are done. But this has this small issue that we need to solve with this LP. And while this LP can be solved fast, but still, it's still not a very easy task. You still need to go and do a course on it to figure out how to do it. So I will give you a different algorithm, which is slightly worse than this, but not much worse. But which is simple and easy to state and has clean ideas, and which also does the same task. So let's go over that. So again, we are the realizable case for now. Okay, so this is the algorithm for today for the perceptron algorithm. Okay, so what does this algorithm do? So it starts from some initial W. Okay, so start with W0 to be all zeros. Okay. Then you keep updating the W after looking at every training example. Okay, so so while there is a training example for which you have classified wrongly, for which YT W inner product xt is equal to 0. Okay, so this means that you have classified it wrongly. So while there is an example like this, you can update the W. Oh, this is WP. So there are two T's here. So one is so by T I will refer to the training example, and I will have an I, which is about the iteration. So I is equal to 0. So iteration 0, W0, 0. Yeah, so at the current iteration, if there is an example which is not specified currently, then you do some update. So you try to make this example a bit better. So you update Wi plus 1. So next W as Wi plus y text. Okay. That's it. And then you, when this loop finishes, hopefully it will finish, maybe, and then you just return. Yeah, so just output the last. Yeah, I'm not writing it formally, but yeah. When this loop finishes, there's some output for that. Okay, so is algorithm clear? Okay, good. So let's try to see what this await is doing. What's going on here? So okay, again I draw a picture. Usually helps. So here is, here's the bit I don't know. Maybe here is the XT. So what's going on here? We are saying that YT times W is WI. XT is less than or equal to 0. So what is this inner product? So this is some multiple of this projection. It's not a projection because there's some normalizing factor here, but it's a multiple of this. So here this projection is positive, right? The angle is acute here. So this quantity is positive, but maybe the whole thing is negative. So maybe the YT was actually negative, -1. So in that case, what does this say? It's saying that let us move W in the opposite direction. So I want to increase the angle between W and X. Right now it's acute. I want to make it obtuse. Right. So how do I make it obtuse? Well, I just add to W the negative vector. Remember, YT is negative. So YT was negative. So I add to W this minus XT vector, which is this vector. And what does that look like? So I draw a parallelogram like this. Here, new W is here. This is look like this. Right? And as you can see, the angle between this has increased, which is what you wanted, right? Earlier, so YT was negative. We want the angle to be obtuse. Initially, it was acute, but this operation has increased the angle. So hopefully, these are obtuse. Maybe it's not yet, but it is already increased. So yeah, so that's what this is doing. So it's just saying that give me an example which is wrongly classified, and then update W in such a way that my angle goes in the right direction. If it is has to increase it. Otherwise, it might also decrease the other way. But right now it's increasing. And because in this problem, only the angles matter, right? So when I say that sine of W inner product X is positive or negative, then I'm really talking about only the angle between W and X. So yeah, so this is playing around with these angles. Great. Okay, but now it's not so clear that this will even terminate. Maybe this goes on forever. Just says that while it will be like this, you update, but maybe this goes forever, right? So I want to prove that this will stop. So that's the main theorem. So a theorem is that. It's the book. You don't want to write longly. Okay. So in the realizable case, so we will give a bound on how many iterations you will take. So that R be the maximum norm of any xi. So max for xi is important xt, right? As we already know of xt. And that B be the minimum norm of W, so that your examples are tightly classified. Remember, we had this thing, right? Binding never at least one. Yeah. Okay. So B is defined like this, and then this algorithm will stop. Then algorithm terminates in in RB square steps. Yeah. So number of iterations there will be at most RBs. Should probably put it all like this. Okay, yeah. Okay, great. So to understand this, so R you can see, you should understand. B is kind of what I was talking about earlier. So notice, okay, so this is true for all D. So what is B here? So B just saying that, let me look at, so here are my examples, positive and negative examples. Let me look at all lines. So you have a line like this, you have a line like that. There are many lines which do the job. Among all of them, let me also take the one with the smallest W now. Yeah. So the many lines will give me this property. Let me further pick the one with the smallest W. So that will turn out to be what is called the maximum margin line. So that will be the line which has the largest distance from the closest point. So for this line, the closest point is this guy. So distance is this thing. For this line, the closest point is this guy. So distance is this. So this will prefer this line. Remember, right? For any line which satisfies this thing, the closest distance of any trailing point was 1 over norm W. Right? That's the discussion which we had. So if I minimize the norm W subject to this condition, then that's just telling me that I'm trying to to maximize this closest distance. So this is capturing that. So B is just the inverse of the closest distance. Inverse of the maximum of the closest distance among all possible lines. So you could write like this, or maybe it's easier to write the other way. Maybe if I just write 1 over W, that's better. Okay, let me write the other way around. Let's call this capital gamma. Remember, small gamma, let's call it capital gamma. And let me call it 1 over W. I think that's going to be better because so maximize the maximum of 1 over W. So this is the case. It's the same thing, right? Now this finishes at R over gamma iterations. The same thing. And it's a bit better to write because this gives you a geometric meaning of it. So so gamma here is is how close your nearest point will be for the best line. The best line is the one which has the maximum distance from the nearest point. So how close will this guy be? That's gamma. So the smaller gamma is, today it means that it is more difficult to classify. Right. So if you have two instances here, okay, very simple. So let's say I have two instances. In one instance, my points are very close. So this is a positive point, this is a negative point. In this instance, my line will have to pass like this, and this is kind of difficult to classify. Right? And it's captured by the fact that this gamma here will be small. Right? But if I had something where I had plus here and minus here, then then my line would look like this. And then I would have a big gamma. This gamma is capturing this margin. It's called the margin of a classifier. So small margin is more difficult to solve. It takes more iterations. And R here is how big your problem is. Okay, so is the theorem clear? Okay, now let's try to prove this. Should I erase this? No, maybe I erase. Okay, I erase this. Okay, so there are essentially two steps in this proof. The first step is remember to talk about the angle, right? So did our angle kind of go in the right way. So the way you can capture that is by saying that so here's the statement. So remember I have some optimal W star in it. So W star is the W which maximizes this. So that is the optimal W. So it's giving some. So this is for some W star. So think of some optimal W star, and I want to argue that my angle with this W star always keeps getting better. So so I want to say that as I iterate, my Wi becomes more and more acute, anchored with W star. So this was my W star, and my Wi was this, and Wi plus 1 will look something like this. So the angle will go down. So it comes closer and closer to the right thing. I may not get here, but I will definitely get closer every time. So that's the first idea. Angle with W star. Okay, let me just write it in math. It's to be faster. So to show that the inner product actually. So Wi plus 1 W star is bigger than Wi. So yeah, so my inner product has increased, indication my angle has decreased. Okay, but you have to be slightly careful because the angle for angle also talk about the norm, right? So maybe my inner product gets better, but my norm has also increased a lot. Okay, so what I'm talking about. So remember that the angle between W and W star is what is a cosine inverse of inner product W W star by norm W star. That's the angle. So I want to say that the angle keeps decreasing. I will not be able to say exactly that. I wish I could say that, but I will not get exactly that. But I will get something very close. I will get that the inner product gets better, but it's kind of in the right direction, right? To decrease the angle, I better increase the inner product. And I don't want the norm to increase by too much. If my norm is constant and my inner product went up, then my angle has decreased. I will not be able to get exactly that, unfortunately. But I will be able to get that the norm will not increase by too much. So, second thing is now W plus 1 square equals to 1 square that must now W by square plus R. Where R was the maximum overall degree of freedom. Now let's see. Okay, so you will get that. And okay, and by how much will this increase? This will increase by how much, right? So let's just write that. So that this minus this is at least. So the inner product will increase by at least 1, and now will not go up by way too much. So kind of decrease the angle, but maybe not quite. Sometimes the angle might go up also, because maybe maybe this increase, but maybe this is just maybe this increase a bit too much. But overall, you will be right. Yes, so these are the main two tricks here. So maybe stay at 10 for that test. Okay. Okay. First of all, let's see why things are enough. Suppose I can prove both of them. Let's say. Then I can get at why. So let's think what happened after t iterations. Let's say I do capital T. So we call capital T. We call it m iterations. At k iterations. So I do k iterations. Then what has happened? Well, okay, so what is the norm of W after k iterations? This is at most what? Can I ever turn the norm of W after k iterations? How much? K times R square. Right? Because initially it was 0. Right? So every time I increase by it was R square, so it was K times R square. Good. Yeah. Okay. So yeah, this. Yeah. So that's this first thing. Or I'll write like this. Some trickery here. Square root k. Good. So that's observation 1. Observation 2 maybe. Okay. Great. Yeah. So now what's the idea? Now let's look at this thing here. So notice that the denominator is W star times square root k. so I want to say that the whole quantity is at least something. So the thing in the bracket. So I want to say that WK W star by K W star. This is at least something. And remember, I want the whole thing to be small, so I want the thing in the bracket to be large. Right? So I want to say that this is quite big. How big is it? Well, this WK is kind of small, so the whole thing is at least the thing here divided by W star times root KR. And what about the thing on the top? So I want to say that this is big enough. How do I say this is big enough? Well, I try to use this thing. Every time I do an iteration, my inner product goes up by 1. So I want to say that okay. So after key iterations, what can I say about this inner product? What were it initially?
Yes.
0, right? Because W0 was 0. Initially, this inner product was 0. Every time goes up by 1. So here, this is at least. So good, right? What is non-double star by the way? So what about non-double star is a replica? This is yes. So yes. So the thing in the bracket here is at least going to be this thing after the iteration. It's going to be pretty big. Yeah. But then the thing is that okay, how big can it get?
I mean, this the right side quantity can be at most 1.
Yeah, exactly. Yes. So this thing can be at most 1. Right. So this thing here is at most 1. And then that tells you, gives you a bound of words. So therefore, K is, to simplify this. So what do I get? So I get root K here, and I get R over gamma here. So I get exactly that. So I get that K is at most R over gamma. So that's it. I mean, we didn't do anything tricky. Just it's that okay. This quantity is getting bigger. Hopefully, at the end of K iteration, it's going to be pretty big. It can never go beyond 1. So you cannot do too many iterations because it keep growing at some point. It becomes very close to 1. So yeah, so you cannot do more iterations. That is needed to make this make this go 1. So yeah, after K iterations, you have this much quantity at least. So manipulate this and 1, and you get that 1. So that's it. No tricks. Yeah, so you know all about the angle, all about this cosine inverse of this. It's all here better. Okay, now I just show these 2 things that we have. That's going to be not very hard. Any questions about this? Like, why are we looking at this? What's going on? You can ask questions here by raising the board.
So you know, like all of this is happening in the realization.
Yeah, everything is realized. Okay, now let's go to both of them. So let's do the first one. So, okay, so what happens when you do iteration, right? Remember, this is what happens. So let's just write it down. So W I plus 1, and then put W star. So W I, and put W star. Plus YT, XT, and put W star. Great. And now I claim that this thing is at least. Why? So it's trivial actually. Because we define W star like this. W star, remember, is W star satisfies these equations by everything. So yeah, that's it. Okay, great. So yeah, this is easy. Let's do the other one. So okay, this is going to be a bit hard because I have to square things. But let's do it. W plus one square is what? This is lambda rho I square plus now xt square. Remember, yt is either plus one minus one, right? So I'm just ignoring it. Plus 2 yt xt net product xt net product what? Yeah, that's what this is. So I threw a yt square here because that is one. Okay, so this quantity here is r square. It's no more than, so this is no more than, you know, y square plus r square plus this thing. I claim that this thing here is always negative. Can someone tell me why? It's very easy actually. It's already on this board.
So X is the point where W misclassifies.
Yeah, exactly. So single that's an important. So that's it. You're done. Prove both of them. Yeah. Don't know too much about the algebra. I mean, that's kind of very easy. The only thing to remember is that we are trying to, you know, maximize our normalized inner product with W star. I want my angle of W with W star to keep decreasing. So I want my normalized inner product to keep going up. So I want the inner product to keep increasing, and I want the norm to not go up by too much because I'm normalizing with a normal. That's it. Totally. Any questions about this? And ultimately, you get this bound, which is also interesting. So R is maximum of xt, and gamma is this. So gamma is a margin. So look at the best line. So look at the line which will achieve the maximum of the minimum distance from any intermediate point. That's what this is. Yeah, let me write in English. It's like maximum of minimum distance from any intermediate point. It's maximum over lines. So look at all lines and maximize the minimum distance from any intermediate point. So that's the interpretation of this word. Okay, so so maybe a few more words. So remember, ultimately the number of iterations which this takes is r over gamma square. So you may think that okay, if r over gamma square is very big, and there's a lot of iterations. So yeah, but typically in practice, this turns out to be not very big. So we must still use this algorithm because it's extremely simple, easy to implement. Whereas the previous algorithm, linear programming, that will always be efficient, but it will sometimes be slower than this. So if this is small, then maybe LP is always slower, and this is also more difficult to. Yeah, so so often in practice people try this first. If it takes too long, then they try here. Also, a couple of more words. So this algorithm is important historically because this was one of the very first machine learning algorithms which appeared. And yeah, the author was very famous by Joseph Clark. Yeah, so it's kind of very interesting algorithm. Okay, great. Okay, I don't want to do any more today because almost time, but I'll just give you some summary of next classes. What will happen? So next time I want to look at next couple of classes. Okay, I want to talk about these slightly more difficult cases. So this was a realizable binary classification case. But what do you do when it is not realizable? And what do you do if it is not binary classification? Okay, so non-realizable case. And the non-binary classification case. Okay. Yeah, so I don't want to go into details today, but I want to just give you, the big picture of what's going to happen. So both of these cases, the trick will be to work with a non-linear objective. So to work with a non-linear objective. So it will not be as simple as it would not be linear. Remember, we had this LP, right? So we had some minimizing some linear thing, 2x1 plus 3x2. So due to some linear constraints, some x1 plus x2. So here is one linear objective. So both of these ideally will be to move to non-linear objectives. They will be non-linear, but they will still be convex. Does everyone know what convex is? Okay, maybe I'll give you a quick overview. You can read in the book, please, next time. So trick will be to go to convex objectives. What objectives they will be, that we will go into next time. But they will be convex. That's the first one. The trick is that convex programming is also easy. It is also efficient. So convex program, can be solved efficiently. And later in the course, we will also talk about one algorithm for this. But for now, it's okay to just live with the fact that we can solve convex programs efficiently. This is enough for today. So next class we will tell you what the objectives are and how to do them in some cases. And later classes we will go into algorithms for doing this efficiently. Okay. Good. All right. Stop early today.